Let's look at an example now where we're going to have repeated eigenvalues. So we have our A matrix. This is written in matrix form. And we need to find the determinant of A minus lambda I to find the eigenvalues. So here's our A. If we find lambda I, it would be this. Notice it's got lambda is down the main diagonal. And when we subtract those, we get this guy. So to find the determinant, I'm going to recopy the first two columns. Three solutions. So hopefully we're going to end up with three eigen. So if we multiply, we're going to have 1 minus lambda cubed plus 8 plus 8. The 8s are coming from multiplying that and that diagonal. Subtract. Now we're going back the other way. So that's 4 times 1 minus lambda plus 4 times 1 minus lambda, which came from here, plus another 4 times 1 minus lambda. So we have 1 minus lambda cubed plus 16 minus 12 times 1 minus lambda. So we're going to have to do some fancy math to simplify this because we've got to set that equal to 0 and then we need to solve it. So let's factor out that 1 minus lambda cubed. That's going to be 1 minus lambda times 1 minus lambda times 1 minus lambda, which is 1 minus lambda, times 1 minus 2 lambda plus lambda squared. So we're going to have 1 minus 2 lambda plus lambda squared. If we distribute the 1, if we distribute the negative lambda, we're going to have negative lambda plus 2 lambda squared minus lambda cubed. So we're going to have 1 minus 3 lambda plus 3 lambda squared minus lambda cubed. So let's take that and plug it in here. And I'm going to change the order. We have minus lambda cubed plus 3 lambda squared minus 3 lambda plus 1, and then plus 16 minus 12 plus 12 lambda. Remember, the goal is to set this equal to 0. So we have negative lambda cubed plus 3 lambda squared plus 9 lambda plus 5. So if we remember back a few weeks ago, we reviewed the rational root theorem. So we need to find our p's and q's. P's are going to be factors of 5. Factors of 5 are 1 and 5. And we have to account for all possibilities, so we're going to use plus and minus. We need factors of negative 1, so that's going to be 1. So if we take every p value and divide it by every q value, we're going to get that p list, which is going to be 1 and 5. If there is a rational root, it is guaranteed to be in that list. So let's start trying things and let's see what happens. If we were to substitute in a negative 1, what do you get out? So in this case, if we substitute in a negative 1, when I did that in my calculator, I got 0. So the remainder theorem says that whatever you plug in, and then what you get out is going to be the remainder. So the remainder is 0, which means we now have a root. So this means that x equals negative 1 as a root And if we wanted to factor this completely, x plus 1 is the factor associated with that root. And we really just need 1. So if we plug that -1 in, we're going to do some synthetic division, and we're going to divide. Really, we're dividing this factor into that cubic. So we're going to multiply, add, multiply, add, multiply, and then add. So this is what's left over. So here's what we know. This characteristic equation factors into x plus 1 times -x squared plus 4x plus 5. And remember, we want to set this equal to 0 and solve. This is going to factor a little bit more. If we factor a -1 out of that, that's going to leave us with x squared minus 4x minus 5. And that factors into x minus 5 times x plus 1. So we have x plus 1 squared times x minus 5 is equal to 0. So we have a double root here. Okay, and that's coming from there. So we only have 2 unique eigenvalues, not 3. But that's okay. So our eigenvalues are -1 and 5. So let's substitute in that -1. I'm going to go back up here, and I need to create some space. So let's start with the -1. If we plug in -1, and remember it goes in for the lambda in the A minus lambda I matrix. So if we plug in -1 in for these lambdas, 1 minus -1 is a 2. 1 minus lambda 1 is a 2. And 1 minus -1 is 2. If we were to do RREF, we're going to end up with 2 rows of zeros, and that tells us we're going to have 2 free variables in this solution. So remember what this says. This says x1 minus x2 plus x3 is equal to 0. And it tells us x2 is going to be free, and it tells us x3 is going to be free. We always want to write this in terms of 2 other variables. So our solution is that, but we need the eigenvector that's going to be associated with that. Because we have 2 free variables, we will have 2 eigenvectors. So here's the way I like to do this. You can pick any values you want for x1, for x2 and x3. Remember, x2 and x3 can be anything under the reals. I like to keep it simple. So if I let x2 be 0 and x3 be 1, then I would end up with -1, 0, and 1. So it's really just the coefficients of x2, the coefficients of x3. And then I could do the same kind of thing here. So we did this by let x2 be 0 and x3 be 1. And you can pick any values. That's going to be the easiest combination. So we could do this something similar here. We could let x2 be 1 and let x3 be 0. If we let x2 be 1 and x3 be 0, we're going to end up with 1, 1, 0. So we ended up with 2 unique eigenvectors for one eigenvalue. So this was a little different than the last example. Now let's substitute that 5 in. Remember, it's going into the a minus lambda I. It's going in for all of these lambda values. Here, here, and here. 1 minus 5 is a -4. We need to do our REF. So if you were to type that in your calculator, here's what I got. So x1 is equal to x3, x2 is equal to -x3, and x3 is equal to x3. The eigenvector would be 1, -1, 1. You can pick any number for x3. The easiest thing to do is let x3 be equal to 1. So our solution would be C1. And I'm going to use this one first. Order doesn't matter here. I'm going to use the brackets again. It doesn't matter if you use the brackets or parentheses notation. I'm good either way. So this came from eigenvalue of 5 and the eigenvector associated with that. Our C2, our second piece, and our third piece will come from these two eigenvectors. So it's going to be C1 times -1, 0, 1 e to the -t. The eigenvalue was -1 plus C3 1, 1, 0 e to the -t. If we wanted to, like we said before, we could write this in expanded notation, which just means we could have an equation for x y and then z.